right, so assignment 2 is due, DUE, in here. It's hard. Assignment 2 is tough. So I'm trying to give you as much of it as I can. Last last two class meetings, you saw how to handle input array. Okay, so here we start for us. This is, what's the date on this? February 12. And this is 240. And page 1. Okay, so input array. No, function was, you know, recently. Now today we'll refine it. And some other things are coming. Okay. The refining comes from input data validation. Okay. The world is full of bad people who want to break software. There's digital thieves and there's physical thieves. Okay, so good commercial software implements data validation everywhere. We want to imitate that and do the same thing. So the strategy is input all numbers into a string. Then run a checker on that string to validate that these string contains real digits. And if it passes the check, then convert the string to number, to float. For us, it's a float. Okay, we need to talk about that right now. And okay. Under that, you got the screenshot. That's what we're going to do. Steps 1, 2, and 3. Okay. Page 2. So we go back to the .bss segment. And we'll say input string is RESB. Pick a nice big number, 256. Okay. So in computer security, they study stack smashing or um, some overflow problem. If the program is programmed to accept up to 256 characters, what happens when some malicious person enters 300 characters? Well, it damages a lot of things, and that's a real bad hack. Okay. So for us, it's a learning exercise. You choose a number here. You choose. If you can read that thing. Okay. Next is there's going to be so we drop down into segment text. And then further down in here, where there's a prompt for input, PROMPT. This is not code. This is just to show what it would happen here. Please enter floating point number press Control D to exit. I wonder if that's going to work. We'll find out. Okay. So here's the block. Input number into string. Again, so it will stand by RAX 0, move RDI string form. Move RSI input string. Okay, that was declared in VSS up there. And call scanner. Okay, so now we have an input, but we don't know if it's a good one or a bad one, if it's valid or invalid. So another block says, validate the recent input. Input. And we have a function that does that. It's called isFloat. So here we go. Move RAX 0. Move RDI, the string number, input string. Right. All is float. Okay, so is float supposed to return a Boolean? And it does. It returns 0 to say to false. Now, I think if this is available download, you don't have to make it. If you read it, the code in it, I think it uses 1 for true, but officially we're supposed to say a non-zero is true. Non-zero is true. Usually true is 1, but not always. It could be 7, and that's still true. Okay, so we we got to test our call is float. Oh yeah, so is float gave us this answer in RAX as usual. Answer in RAX. Answer RAX. So we got to check what's there. Compare RAX with, say, 0. If those two are equal, we have a bad input. We have to get out of this area. We'll just go to bad. If it doesn't jump to bad, then we have a good input. So down here is convert. Good string to real number. Okay, how can we do that? We have a conversion function. So again, move. Yeah, I admit that this statement is redundant 80% of the time, but there's sometimes it occurs where it's really important. Okay, so Rx is 0, and ATOF, I never gave this digress here. ATOF is has a prototype, double ATOF, and it accepts null terminated strings, char ST for string, and it's like that, like that. So it has one input parameter, RDI. Move RDI. And what's our string called? It's called previously input string. Looks all right. Call ATOF. Now, oh yeah, and it's returning a 64-bit double. That's going to be returned in XMM0. Okay. There's only two registers that can return something from a function. RAX, if it's returning an integer class of value, XMM0 if it's returning a float type value. Okay, so that's sort of that completes the objective here, is to show how to validate for, oh, and no, it's not complete. It doesn't handle, what happens if it's a bad one? Okay, it's here, jump to bad. Oh, I don't know that answer. Anybody have an idea? Okay, so here is bad. Okay. Printf. So this is comment territory. Printf says, please enter that number again. Okay. And then how's it going to do that? It has to go back we're going to send it somewhere. I need to put a name here. Can't squeeze it in. It's right in there. Begin input. So then we say JMP begin input. Okay. I want to make sure it's logically correct, and then we can try work on making it look pretty. But so if it discovers a bad one by is float, it takes us to here, to bad, right there. The instructions are try it again. It takes you back to the start of all this to input the second attempt. You set that up, you call scanf, and then you validate it, and you check for it by using is float. And if it's bad again, it reaches this point, it jumps to here, says try it again. The user is stuck until he or she gets it right. Okay. So what now? This is a part. Suppose you make a proper conversion, and the last step is to put it into the array. So I need a I need to JMP insert in array. Now I can't have all those spaces in there. Insert in array. Insert in array. Okay. Yeah. Move. I'm trying to recall from last class meeting. I think it was R12 plus 8 times the index 1. I forgot the index register. R10, comma, and where's our good number? Oh, this is programming. I left out a piece here. I almost feel bad. I should rewrite this page. Call ATOF. There's something to do. You know, you're going to look at this in a couple days from now and say, what was he doing? Okay. This is worthwhile. 3. Okay. I'll get it right now. CMP RAX 0 jump to bad. Now convert. String to number. Okay. So far, just copying what was there. Move RAX 0. Move RDI input string. Call ATOF and ATOF puts the converted number in XMM0. Did I need to do anything more in here? Maybe I did. Maybe it's okay. at this point, oh yeah, we that blue ink needs to be there officially. JMP to insert into array. Insert in array. Here's the bad part. Bad says enter another number. Output enter new number. And JMP to do it all over again. Begin input. Input. This looks cleaner by a little bit. And then insert into the array. Insert in array. ATF, it's still when indexing M0. Okay, I almost had it previously. Move into R, I have to go back to the last class meeting, I think it was R12 plus 8 times R10 X M M 0. Link R12, R10. Okay, so when you see it later, in this context, R12 is it is the array. R10, as I've used over here, is the index of the array. I hope those are the same registers as last time, but the form is usually about the same. You name the array at the beginning, and you add 8 times 8 for 8 bytes in a cell times the index number. And then this goes here, and then we increment it, the index one larger. Okay, this was almost right, but I like, this is cleaner. This shows what's happening.
The insert array needs a colon, right? Or no?
Yes, it does. Thanks. Right. Bad. Jump to bad, not here. And not here. Okay. And the function ends. There's some pops, 16 pops. And in this whole assignment, number 2, I can only tell you, the hardest work is the input array. Did I have a picture of the diagram? The rest of the diagram is here. This one is a bunch of work. Okay. This one I can show it to you in 10 minutes. And summing the array is 5 minutes. And outputting the array is just a loop that goes through the array from the beginning one by one and calls printf. So we got to get this one, this block down here. Okay. I think this is it. Let's back it up. We're going to start earlier than that. Here's the strategy. Okay. Here there's some declarations up above, but like external ATOF. Yeah, for one instance. Right. If you forget the external declarations, the assembler will tell you that it doesn't understand scanf. Okay, so you add a extern scanf. Okay, that's data validation. Now I think I think it's logically correct, class, but I think it's kind of sloppy spaghetti. You think that's let's analyze it. I think it's okay. I haven't done this in advance. I didn't do it last night like I usually do. Input array. First thing that happens is prompt for numbers. Okay. Second thing that happens is this block. And F into string. That's okay. Then call validate. Not call validate. Call is float. Is float. Okay. Yes. No. If it passes the is float test, that would be next page. You check for zero. If it's fails it, it goes execution goes down this side, and if it passes, it goes to a conversion function. Convert ATOF. ATOF produces a value XMM0. Okay. Copy XMM0 to array. Increment R10 plus plus. That's why. I told you, even for old people like me, you never get it. Okay, what's missing? You only get one number in your array. Okay, like it came out of the diagram. This was going to lead to return. On this side, if it's no, that's the bad. So there's try again message. And then it says go to resume here. That appears to be right. This one's missing something. If you get the first good number into the array, you don't just quit then. We have to take this somewhere else. This one we need to go here. Okay.
Can you move the paper?
Oh, yes, I keep forgetting. The diagram, the diagram reveals something, but it doesn't reveal the exit. The exit is when scanf attempts to read your data, and it's a control D. How's our clock set? Okay. You with me? We'll solve this out right now. I didn't do this one in advance. I should have last night, but I didn't anticipate it. Okay. So when you call scanf, if the input is a control D, then we're going to exit out of this whole thing. Let's diagram it again. Okay. So just to show this is second attempt. Let's do it in blue maybe. And I try to stay under this camera. Would be here. Okay, I'll try again. Input array. That's a cool blue. Okay, showing better. Okay. The next thing is a prompt for a number. That usually translates to a block of code somewhere else, a block of assembly that ends up calling printf. Okay. Then there's another block. You set up scanf. Call scanf. Okay. CNPL plus D. Did we get a control D? Okay. If yes, which side shall I run this on? I'll try. If yes, then I don't want, I'm afraid I'm going to have lines cross over, which is not a good picture. But if yes, we go towards, what's at the bottom? 16 pops and return. Okay. If it's not a control D, that says no, then you call is float. If it says no, it's not. Let's do it out this way. If no, then it goes to a message that says try again. Input it. Try again. And then try again goes back here and prompts again. Okay. So the user has to get it right eventually. It goes down here and it's a real string, and you check it with is float and it's false. It's not a good float. So you go back through this again and again. A user may give up and press Control D, in which case you get out of this. Like, no. What about it here? This is the yes. Okay, it was missing in the last diagram. So here you do a convert, using ATOF. After which that produces XMM0 with the inputted number. So you put XMM0 into the array. And increment the index. INC, whatever register that was. Okay, then we're not done. This has to go out of, I don't know where to draw the lines. It doesn't look pretty to go out here, but we'll do it anyway. I think that's complete now. Uh, so there's a prompt, and you read in this string, and you check it. Oh, did scanf give us a control D? If so, you're about ready to come out of this. 16 pops and you return. If there's no control D, you test the inputted string and find out, is it a valid string for conversion? If it's not a valid string, it contains character letters in it, for instance, you go back and try again, discard it and try again. You go through this cycle until finally it's correct, it passes the test, is float. At that point, you call the ATOF, called in a conversion function, and that produces an answer in XMM0. Then we want to copy XMM0 into the array, and right after that, we increment R12. Now you're ready to go back and get another one. And you go back here and go back. Same thing. I think it looks okay now. You call scanf. Scanf is not control D, so you follow through this pattern again. This little inner loop will repeat until the user gets it right, and then the string it gets converted, and then it is placed into the array, and you increment the index, and you go back through there. I think logic is correct. I don't know, how do you debug logic in complex programs? I didn't realize that until I saw this, that it was not putting the second number, it was only putting the first number and quitting. So I added that line to show it. Now, I think this is a better version of it. Any questions, anybody? Let's see, I had a topic here. It's oh yeah, we got to talk about the sort today. Now, I assure you that computing the sum of numbers in arrays is Mickey Mouse compared to this thing. Outputting the numbers in the array, just running a equivalent of a for loop, is very easy. But there's a small challenge, not as bad as this one, in the sort function. Let's do it right. Okay. This is now page 4. Page 5. This is all about sort. Okay, the instructions say, gotta find my copy of it. There it is. Okay, it says do it in C++. I'll do it in C language. So I last night I Googled for an answer. It said this. This is one. You can choose selection sort or insertion sort or anything that's an easy sort. Double name of the array is A and long size. Size is how many elements are in the array. And no, so uh, it's, it's working. Okay, I'll tell you what I saw, but you could use anything. They declared integer pass, integer j, integer hold. And then there were two for loops, one inside of the other. For pass equals 1, pass less than size minus 1, pass plus plus. Okay. And then there was a for loop inside of that one, which is okay. We don't care about it. Just copy something that works. 0, j less than. It says less than or equal. I don't know what. I'll put what I copied. Size minus 2, comma, j plus plus. That's a j plus plus. Okay, and then if the two elements are out of order, if a j is out of order with a its neighbor, then you swap those two. Swap a j and a j plus 1. A j plus 1. But the problem is swap is written in assembly. Okay. And again, you're free to pick a different sort algorithm. Just copy it from any place that looks simple. But don't do quick sort. It's more complex than necessary. Okay, so we faced a problem with what is the function swap? Here is, I don't know how to write this prototype. Void swap. Actually, this doesn't work quite right. The swap double x, swap double y. And actually, doesn't even work because these are passed by value, and passed by value doesn't change. You can make all kinds of manipulations with x and y, and they don't change by value. They don't change themselves. So, but I'll show you that it does work. I mean, because it's assembly, it will work. We'd like to imitate this. We want the y and x to change their values accordingly, because in data structures class, when you learn sorting, there were some swap statements in here. There wasn't a call. There generally is not a call to a function to do the swapping for you, but we're learning stuff. So let's make an assembly function. Let's, okay. Genuine function. Here's license agreement and global swap. I don't think we need anything else. And then segment dot data is empty. Segment dot BSS is empty. Segment text. This is not compilable. There's no SEG. So, but we're laying out the plan for a function called swap. Okay. Now, this is an array of float numbers. Right there it is. It's an array of float numbers. Each one of these is a float. So you're passing a float 1 and a float 2 here. Guess which registers they go to? X0 and XMM0 and XMM1. Okay, so I'm shortcutting this to get to the heart of it. When execution begins, oh, here's swap, SWAP. When execution starts, I know there's 16 pushes, but that's not our interest. The two registers XMM0 and XMM1 arrive holding two numbers. I'll make that a comment. XMM0, XMM1. Is this going to work? XMM1 hold two numbers. Okay. We'll all learn something out of this. Okay. Okay. Segment text. Oh, we're in segment text. Sorry. Okay. Here's a technique used in assembly, but we'll have to figure out if this will carry back to C++. The technique for swapping two registers is XOR. So it would look like this: XOR PD XMM0 XMM1 XOR PD XMM1 XMM0 XOR PD XM0 comes XM1. Okay, we're done. The amazing thing is XOR can swap two numbers without using a third temporary place. It can just do it with itself. Now, 16 pops in return. Okay. What I don't know, and I need some help. Here's the function swap. This is just nothing up there. These two arrive. That's passed in data. We swap their values. There's XMM1, 0 and 1 have the opposite values than when they started. But does the array get it back? Does the array that's full of float numbers I don't think so.
Doesn't sound like
No, it doesn't sound right. does pass by value, you get a copy into the called function. The copy can make changes, but they don't go back to here. Oh no. They don't go back to these two variables that we want to change place.
Why can't we just have like the swap function within our input array function as like another
Uh,
instead of going back and forth from the C file?
oh. Okay, part of this was supposed to be educational that shows you how C can call assembly. And actually, I know that the driver is in C++ and it calls assembly, but it doesn't really do anything, doesn't pass anything significant. This little example was supposed to show that a function inside of this, by eyesight, you don't know if this is C or C++. They look identical. But we were to show that a C++ source file could call a function written in assembly and swap these two values. But pass by value means that the parameter in the caller gets copied to another variable in the call function where it performs changes, but it doesn't go back. No, there's a flaw in the instruction. That's those in. Okay. Okay, is there anything we can do about this? It is out of sync. P. I have an idea. Let's see. Last 10 minutes. Okay. We have to pass it by pointer and see if that works. What do you have to? Okay. Array of doubles. Okay. Double small. P. Yeah. This is a shot in the dark. Let me try it. Star P plus J. I'm reproducing this sentence here. It's greater than P reference P plus J plus 1. Then they're out of order. Then P, P, oh. So P plus J and P plus J plus 1. Okay. How does that work? Okay. Back to the theory of
Like we just need to use the by reference, right? The ampersands before the variables.
Oh, is that, maybe you got it.
So when we're calling our swap, it just needs to be reference to the stuff.
Before I go into this messy thing, let's see that. J, never seen. A, J plus 1. So you send the address of this guy, and the address of this guy is sent to swap. And what does assembly receive then? It receives two addresses. So this is
Then instead of swapping the values, it just swaps the addresses, right?
yes, you dereference. Yeah, let's do it. So these now addresses, these are not floats. These are general purpose registers. That's RDI and RSI. Okay. And now swap segment TEXT, swap here, and we receive RDI and RSI have addresses. So I'm going to do this. Okay. Dereference. Okay, where should I put it? We got to experiment. Move SD XMM 8, comma, RDI. Previously, you've seen me dereference RSP and get a float number off the top of the stack and put over there. That's 8. And now move SD XMM 9 RSI. Okay. And now those two numbers are over here, 8 and 9. We need to swap them under traditional methods. How should we do it? There's going to be 3 moves. MOV, SD, X, XM15. XMM15 is our holding value. XMM9, move SD, XMM9, XMM8, move SD, XMM 8 gets XMM15. I think that's a traditional swap. Okay. A copy of 9 is placed in 15 for safekeeping. 8 overrides this one. Then the copy of 9 overrides 8. Okay. Okay, now let's put them back to where the pointer is pointing to. So we move the two are exchange values up here. Move SD RSI. That was once the first one. How come I got this line? Okay, RSI had XMM9. We'll put it back. XMM9. Move SD RDI. We'll put it back. XMM8. And I'll try and draw a picture of it. I think we're done here. 16 pops and RET. Yeah. Oh, so here's the call statement. Black ink right here. See, how can we make a picture of that? Um, well, first of all, these are numbers in an array. The array is A. And here is, this one right here is number J. And this one over here is J plus 1. And this is sitting in memory. These are indices, but underneath are addresses. There's 8 addresses for each number. Okay. So by using ampersand AJ, we're getting the address from RAM where this thing is sitting, specifically the first one, the first byte. This is the address where that first byte is. And this one has a first byte. And this is ampersand AJ plus 1. Address is a lot. At its worst case, it's 16 hex digits. It's a big number. It can be in the billions. Okay. So what this is, I mean, it's a complex symbol, but this is an address. Address 1 and address 2. Okay. So these two addresses get passed to the swap function under the names of RDI and RSI. It came from a call here. Call swap ampersand A J ampersand A J plus 1. So we want to, this works, but it's too complex. This is logically correct. I can see a simpler solution coming. Okay, so here's address 1, and it points to a float number. We don't care. 3.75. Here's address 2, and it points to a float number, 2.99. Yeah, we don't care. What I did was dereference this and move it over to XMMs and then change their values there. Why don't we just change the value so that this one points over here and this one points over there? If it's simpler. I didn't know what it was. Okay, so here's swap arrives. This is second revision. Segment text swap. Okay. The important information is RDI, this is a comment, RDI and RSI are pointers to float to two floats. Okay, so let's do it here. Move. What should we pick on to be the holding red? RAX, RDI. Move RDI, RSI, move RDI, RAX. Okay. And now RDI, after this is done, RDI points to the data that RSI had. Do I have? It's this picture up here. After this number has been placed in here, and this number has been placed in here. So the picture is now that first address is, points to this one, 299, and address 2 it points to this one, which is 3.75. Okay. The numbers themselves are still stationary, but these two point to them. I think that's got to work. There's a thing called sorting by pointers. There's a thing called swapping by pointers. I think this is the latter. Okay, so over here, that first one is address 1, that whole piece. This is address 2. And now when you come back and you take off, it comes back. This one, this address has the opposite guy's data. They've switched the data they're pointing to, but that's okay. It's part of an array being sorted, and the array feels, how can I explain that? Yeah, the array sits in memory in address order, but we're, okay. Can I try one more time? Here's the array. There's a double and 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 a double. Okay, here is cell J, J plus 1. Okay. This has a, okay. We have to look at the underlying address scheme. So the address of that byte right there is ampersand AJ. The address of that byte at the start of the cell is ampersand AJ plus 1. Okay. And what we've done, we can't change underlying addresses, but we can change what they, hang on. I feel I'm right. I don't know how to explain that. That's the address underneath, a big number, and there's another big number. I don't know how to, I don't know how to explain it, class. Okay, I got this weekend. I'll run this program, just the swap, bubble sort, and we're going to swap. I'm going to swap this way, and we'll see what happens. Yeah, this is a passing of addresses, but no, maybe this diagram's wrong. Uh, yeah, it looks pretty good. I'm still
I
trying
found
to,
it online.
you found it online? Well, then it must be really good. Hey, don't go away now. You want to present it? For sure. The whole class. Okay. You may have solved the problem. Let me find that one.
If I read it bigger.
I'll do it quickly. Okay, so we.
Loads the pointer into wraps for the first removal or for the first location, and then RCX.
The actual
The
date.
address of RSI.
It's, yeah, it's good so far.
Location or you're moving RCX into the location of RGB.
Yes. I'm convinced. I'm being convinced. Okay. Thanks.
The first two are loading the addresses into wrapping the RCX, and then the second ones are storing the value of that location. Or sorry, the value of those pointers into the location.
Yeah, it looks good. Okay, don't give up, everyone. We programmers don't give up. This looks good. Okay, so what was it? Okay, so the call was swap ampersand AI or AJ, that's ampersand AI plus one. When the call is completed, this goes through RDI, and this gets copied into RSI. Okay, so your classmate here has found this solution. Move, comma, dereference RDI. That's the actual number at slot I. Move RCX RSI, the other number RSI. There's two more lines, and then we'll draw a picture and see if that makes sense. Okay, so RDI RCX and S AX. You can already see something being swapped here. RDI is affiliated with RAX, RSI with CX, and now they're switching. RCX goes to here, and this one goes to here. So let's see if we can make a picture out of this. Okay, in the array, there's a number 3.5 at this place in the array, and its neighbor is 2.7. They're out of order. Okay, so oh yeah, so I don't have to show it. The address of 3.5 is placed into RDI. RDI. The address is a mess. 35710, something like that. And the address of this number in the array, RSI. What's in there is another address number, 47FB. Oh, they're probably close together, but apart from that, okay. Okay, that's the address number. At that address, which is stored in there, there is actually the number 3.5. And at that address, there is actually the number 2.7. Okay, let's follow the steps. Dereference RDI, and you get 3.5. RAX gets 3.5. Next one, dereference RSI. Dereference this messy address, you get the number 2.7 and put a copy in RCX. Great. Okay. Now it says the 2.7 gets placed where RDI is dereferenced. RDI dereferenced is here. Let me do it in blue or something so it looks different. 2.7. The next one, copy what's in RAX 3.5 to where this address dereferences to. 3.5. Okay, and then we're done. Now, when we go back to the array, it's back here. What is AI? And it's RDI dereferenced. It's 2.7. Can you follow that? This address is sitting in RDI, and you dereference RDI. What is it holding in A? It's this one right here. And over here, take away the ampersand. Did I say that right? It's RSI. You dereference RSI, but 3.5 is now sitting there. It's looking good. It's they're swapping those two values. Okay, and here's the solution in assembly. Okay. So can we turn that into a nice function? A nice assembly looking function. What's the name of this? This name is swap. Global. And do we declare any of that? We declare that. I don't think there's anything else to declare. Segment data. We just documented it, that we know it's there, empty. Segment BSS, empty. Segment text. Swap. And you do these four things. The first value is an address. It's passed in under RDI. Let's document that here. RDI receives address of first argument. RSI receives address of second ARG. Okay, and then come the four executing statements. You already have them, so let's see. RAX and RCX are just arbitrary registers for temporary holding. It could be anything else not currently in use, but we'll stay with that. RAX, RD. That means it gets the actual number that RDI, the first parameter, points to. It's the address, but it's not the address in here. This is the actual number, 3.7 or something. For the other one, CX gets the actual number of the second argument. Now, RDI is with brackets on it, is the actual number. RDI is the actual number in that first parameter, but it gets the number that came from the second, RCX. And RSI with brackets around it is the actual number pointed to by the second parameter. It was, but now we give it the first value. These are in reversed order from what they came. There's nothing to return here. This swap has void type, return type, 16 pops and return. It's a good exercise, but it's not. You have to think it through. And this is great. Okay, it doesn't even use XMM registers. That's even better. It is really clean. Okay, now I'm sure we overshot our time, but it was worth it. Okay. So this is not where these all start with. This is in the tree diagram. It's not a tree. It's a graph diagram, usually called a calling structure. This one right here. Okay. The sort easy. You just get a copy from the web. But when they swap registers, when they swap array values, call a swap. But the swap is written in assembly. And I think it's all here. This screen. I tried to play a little diagram with that, and I'm convinced it looks good. So, thanks for finding this. Okay, well, we better end, everyone. We're trying to build this diagram. I think it's easy now that we were provided with the solution. This one is still hard. That has become easy because we know the answer, and adding things together is you take one register to be the sum register, set it to 0, and then go through the array, adding each number to that sum register. That's not hard. I'll put the array. You're going to set up a loop that goes through the array one by one and outputs the number. That's not okay. Okay, everyone. I think that's the end of the lecture. It would turn out to be more than I thought it would be, but we've seen it. And I'll stay here until almost 12 noon. Have a good day. you're welcome to stay here and study until 12 noon. Well, that is.
Professor, are we gonna have access to our assignment grade? Are you gonna get emailed to us or something?
Oh, yeah, no. Well, the way you'll get it is there'll be a document that has last four digits of a CWID and then a score, 18, and then a reason, missing header or something. Okay, everybody's on there. You'll see your CWID number, last four digits, and your score. And then it's usually a 2 or 3 word comment, just fine. Okay, and this will be publicly available. It'll be posted, and you'll see your scores and a slight explanation why you got that score. It usually takes about 1 week turnaround time. But we'll see. These are new guys working on grading, and we'll see how good they are.
I tried a bunch of different numbers.
Pretty rate is where we're taking. How many, what the size is before we start using.
Yeah, it should be called max size.
Oh, max.
Yeah, it's how it was declared.
It didn't say that. Yeah, it didn't say that we needed to. They have two, because it was their second assignment, which is what we're doing now. In fact, he specifically said we didn't have the. No. I'm not gonna do any work. I'm a minimal work kind of guy. You want to do more work, maybe.
That's not weird.
This one. This is good, but I think it's different. You think that?
It makes sense though, because you just said plus one. But then also, wasn't the issue with this block where you made it with that extension, right?
Oh.
Isn't that the issue here was that you're just changing the value directly?
Yeah, that's what I was trying to do at the beginning.
But it probably doesn't.
But doesn't this also change the value directly?
No, it changes the pointer directly. There's a slight difference. It changes the, I'm not sure.
No, because like, it would, but then you dereference the pointer here.
Yeah, we do, to get to the actual data.
You have a different way to do it?
He has a 3-line version.
Can I see it?
Well, this is what he showed us.
I showed it to him.
Like
Yeah.
just do the pointer directly, but then isn't the issue with this one is that you change the value directly? Isn't this also changing the value directly? Because you dereference them.
It's just moving the values to different locations, but when the function gets it back, it's just gonna recheck the address. Not, so that now the value at that address has changed. So maybe the original one works too. But.
How
Yeah,
about
makes sense, yeah,
you do that first one,
and I'll do the second.
and you'll do the second one, and